Hi everyone, my name is Johannes Pfleging. I'm from ETH Zurich. I studied mechanical engineering and now I'm working in this project on robot-aided microanalysis. And I would like to thank this committee to give me the opportunity to present the first results of our project in this conference. Let me start with a small repetition of what we already heard in this session. In general, it is important for experiments to control all relevant parameters. For useware experiments, we can categorize these parameters in, for example, 3 categories. On the left, we have the materials of the workpiece and of the tool, like hardness, surface roughness, etc. These parameters are easy to control, rather easy by simply selecting appropriate materials. On the other hand, the duration of the experiment very much influences the amount of MER which is created. This can also be controlled by measuring the time. The more difficult parameters are the parameters of the gesture and the motion itself. Force, velocity, and orientation of the tool also influence how the wear pattern is created. Those parameters are more difficult to control, and fairly little work is done on this side. That's why we started this project, where we would like to use robots in order to have control over these parameters as well. This illustration shows our vision that we have in mind about robot-aided microanalysis. In the center, we have the hypothesis that's about the function of a tool that you found on site. Then the idea is to design an experiment and in lab perform this experiment. Then do measurements of the tool and analysis and interpretation of the data that you saw on the microscope, and storage of this data in an appropriate database. And then if you can evaluate the results and do a refinement of your thesis or not. This is probably familiar to you. The new part that we like to work on is the experimental part, by using machines and robots for the experiments, and also to introduce some sort of automation in this process line here, in order to have to easily be able to perform many experiments, which we believe is necessary in order to have statistically sound data sets to make inference about tool use. We started with this machine. This is a KUKA industrial robot arm. The nice thing about this machine is that it comprises torque sensors in each joint, which allow you to specify certain forces at the arm tip. We attached flint flakes to the arm tip and implemented scraping tasks, 2 scraping tasks and a sawing task so far. We performed these tasks with specified force profiles, which are applied by the robot to the piece. We started with a first study of different flakes, where we performed these tasks on various undergrounds. We used wood of different hardness, also sandstone. It is also possible, thanks to these force control abilities of the robot, to perform these tasks not only on flat surfaces, but also on unstructured undergrounds. Unfortunately, it's a bit slow, this video. For example, in this case, we tried it on bone, and you see that round surfaces are you're also able to perform this on, as I said, unstructured undergrounds. Okay, this should continue, but for some reason I can't show you the rest of the video. Okay, here we go. And you saw that we had rather straight artificial motions, but with a robot it has 7 degrees of freedom. We are also able to include some sort of variation. Here we vary angle and position, transversal deviations in the position. Also curved path are able to implement, which is only a matter of the program that you run in this machine. The hardware is designed to perform various kinds of motions in 6 degrees of freedom in the workspace. The results of this study were measured under light microscope up to 40 times magnification, and also under the SEM. The first row shows a sequence of experiments performed in intervals of 40 cycles, and you can see how the wear pattern evolves. This was done on sandstone. The bottom left image is a SEM of polish, which was created on wood. And what you probably cannot see is that we even see small striations on this scale too, which I have so far not seen on the literature yet. On the bottom right is an image, you can see striations, and due to the straight motions which were performed on these samples, we have very regular pattern in this case. For the variable motions, you can see a clear difference. These images are also performed on, these samples were used on sandstone too, and here the striations vary in the direction, as you can see in this case. Still, these are, as I said, are rather artificial motions, and we would like to know how humans perform these tasks. And that's the part that you don't see with the raw eye. That's why we performed this measurement, where we measured forces and torques applied during the task, and the position and orientation of the tool itself during the task execution. Unfortunately, the video is not run properly, but here you see what we did. Basically, we performed scraping task in a pulling motion and in a pushing motion, which is in this direction with 2 different hafting types on fresh and dried sheep hide. This is the setup we used for this measurement. We have a force sensor here, the silver part, and a position and orientation measuring device consisting of this tag and the video camera. And this tool allowed to switch between 2 different hafting types. The data that we gain with this measurement looks like this. This is the position measurement. We have the up and down measurement in Z and back and forth movement in Y. And you clearly see can identify 2 cycles. During the contact, the Z position is constant, and when you pull back the tool, that position rises. Similar, the Y position varies between the initial and the end position, and when you pull it back, you move back the Y value. The angle shows a similar pattern. Mainly the pitch angle is excited, which is the angle between the haft and the underground. The other angles in this case were not, only rarely, slightly excited. The force measurements also show this pattern, 2 cycles. We have a main excitation in direction alongside the haft, which is Fx. And this was a typical profile that we saw, that the value increases slightly and then reaches a maximum and decreases. Similar the torque. Here mainly the torque in Y is excited, which is the torque which you would excite if you bend the tool in this direction. Then we use this data to feed this to the robot in order to perform the same force trajectory. And when we look at the actual data that we can see then on the robot, we have this comparison. Here I I show one cycle of the robot and 2 cycles of the human, and we see that we can pretty much match the same force profile as which we saw in the measurement of the human motions. Another representation is the trajectory plot, where we have the path of the tooltip here and the force vectors plotted during the contact as black arrows. And we see very nicely that we can have a regular pattern of these force vectors performed by the robot, and also the orientation of these vectors match rather well. To conclude, in the first part, we can reproduce the human data fairly well with the robot. We are able to parameterize certain motions with the robot. It is fairly easy to generate many data sets with the machine, because once you set the motions, you can let the robot go. Also, issues that are remaining is how can we perform realistic motions with this machine. One approach which we would like to follow in future is make use of learning algorithms, where you can set a metric and let the algorithm search for the ideal motion that optimizes this metric. As a little side note, I would like to show you what these measurement data can be used to as well. This is part of a publication that we recently published on +1. Here I compare the 2 gestures using 2 quantities, namely shear force and hand torque, which can be used to characterize both gestures. The shear force is a quantity that you get when you project the total force vector onto the horizontal line of the underground. And this component is interesting because it tells you, because it is the part which is relevant for the removal of material from the workpiece effectively. The more shear force you can apply, the more effective you can be in removal of material. And by comparing these 2 plots, you can already see that in the pushing motion you have in general higher forces, and also the angle is slightly lower. And this means, or we interpret this as an advantage for the pushing motion. And in the statistics, we generate statistics where we averaged these force values and looked at the box plot, and here we see that in general we have higher shear forces for the pushing motion compared to the pulling motion. When we look at the hand torque is we calculate the hand torque as the torque you must apply to the shaft in order to keep the tool in a certain orientation. We saw a similar behavior. The pushing motion also requires higher hand torque in order to perform the task. In this case, the hand torque is a disadvantage, we say, because it requires more energy from the user in order to keep the hold and to keep the tool, and it can lead to tiring if you perform the task for a very long time. So as a second conclusion for this part, I would like to say that the pushing motion generates higher shear force but requires more hand torque. And this might be the reason why you find different hafts and hafting types or gestures in the Alaska, or hafts that you can find in Alaska, and gestures performed by the Chukchi in Siberia. So overall, I would like to summarize that robots could have a significant contribution to the experimental useware science, and also that measuring high quality data of gestures can be very useful to interpret and analyze the physiological properties of different motion types and gestures. Thank you very much.